respected scientific society in the world. Jocelyn was elected by her peers as a fellow in 2003. In 2010, they awarded her the Michael Faraday Prize for excellence in communicating science. In 2015, they awarded her the Royal Medal for outstanding contributions to applied science. The Royal Society commissioned her portrait for their headquarters in 2020. In 2021, awarded her their most prestigious scientific prize, the Copley Medal, for sustained outstanding achievement. Jocelyn joins Darwin, Einstein, Hawking as previous deserving. He is an ardent supporter of women in science, and in 2018 was awarded the $3 million Special Breakthrough Prize in Fundamental Physics, which she donated to the Institute of Physics to help fund female, minority, and refugee students to become research physicists. This year, King Charles III appointed her to the Order of Companions of Honor for her outstanding achievements in science. The Queen of Pulsar's talk today is Tick, 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 Pulsating Star, How We Wonder What You Are.
So is this microphone working? I think it is. Yes, good, great. Thank you all very much for turning up on a Saturday. Weekends are precious, and I'm impressed how many people are here. So thank you for giving time to this meeting. Okay. Right. That's a pointer. Brilliant. New? Oh, you can use the buttons on the computer. It's probably simple. Not to worry. That's fine. Yes. So I think a lot of you maybe have done some radio astronomy and don't need much of an introduction, but for the benefit of those who aren't so familiar with it, I'll say a little bit about radio astronomy, a little bit about quasars, but of course they were mentioned in the last talk, so you've probably already heard a bit about that. Then a bit about being in Cambridge, and in case you didn't know what pulsars were, a few words about what they are. So that's loud. Is that because I'm? Yeah. Right. Am I still heard?
Yes.
Yes. Okay. Good. So the electromagnetic spectrum. Familiar with light. A number of you I know are familiar with radio. There's infrared, there's ultraviolet, there's X-rays and gamma rays. And these days we do astronomy right across that spectrum. Different techniques in different parts of the spectrum. For instance, in X-ray astronomy, you have to put your telescopes on a satellite because the Earth's atmosphere cuts out X-rays. If it didn't, we wouldn't be here, or we'd have lead skins or something. But radio astronomy, we do mostly from the ground. When you get to very short wavelengths, like millimeters, it's a good idea to be in a dry place, and that quite often means high altitude. But radio you can do from the ground. That's it, the right bit. Thank you very much. This is Jodrell Bank, as I'm sure you know. It's a gorgeous photograph. And yeah, when you get the sun close to something, when it's low on the horizon, you realize how big it is. When it's high up at noon, you don't kind of realize the size it is. And of course, this is the big famous Jodrell Bank radio telescope as well. Ah, clicker works, thank you. Right, So, as I think you've probably already heard at this meeting, radio astronomy was developed post-World War II, came out of the work done by radar experts. There had been one or two hints during the war that there were objects in the sky emitting radio waves. It's said that the Japanese were extremely bothered by some peculiar enemy stuff that was low down in the east in the morning, high in the south at midday. So it was known back then that some things at least gave radio waves. But radio astronomy really developed post-World War II and driven to a considerable extent by people who'd worked on radar during the war. And it's turned out to be a wonderful field. Even with the simplest radio telescopes, they were picking up half a dozen different things in the sky. And with today's radio telescopes, it's thousands and thousands of things that we're seeing. So it's been very exciting. Some of the strongest things picked up to begin with, good strong radio signals. When they asked the optical astronomers, what is there? They'd say, well, there's something that's a bit like a star, although it's not a kind of star we've seen before. And it became known as quasi-stellar radio source, or quasar. We now know that they may look like stars, but actually they are extremely distant, and they are a massive black hole, maybe 1 million times the mass of the sun, with material falling into the black hole and radio waves coming from these quasars. But at the point that I started, there were not many quasars known. They were known. There were perhaps about a dozen, something like that. And my particular project was to find more quasars. But let me first give you a bit of personal background. You've probably already noticed my accent. It's not Southern English. I started life in Northern Ireland. I had quite a lot of my education at a boarding school in England. I went to Glasgow University, and then I went to Cambridge. And going to Cambridge was quite a shock. You see, numbers 1, 2, and 3 are all in the north of the country. The south is a different country. I'm sorry, a lot of you may be Southern English, but if you come from the north, it's different, speak different, and in Cambridge, they behave different. Cambridge was full of young men, a bit like Boris, although I know Boris went to Oxford. But if you think of a whole lot of Boris-like young men strutting the streets of Cambridge, little groups talking in terribly loud voices about what Hegel said, what Hegel didn't say. And I'd come from up north, and you didn't behave like that up north. And I thought, oh my God, they're all terribly bright here. It's totally taken in initially. They're terribly bright. I'm not that bright. They've made a mistake admitting me. They're going to discover their mistake and they're going to throw me out. Now, for younger members of the audience, if you ever feel you're in that position, don't run away. Take a deep breath and say, they're going to throw me out, but until they throw me out, I'm going to hang in here and do my very best work. So I was working like the clappers because I knew they were going to throw me out and I wanted to do my very best. And actually they didn't throw me out. Surprise, surprise. So I'm being very, very thorough. Did a bachelor's degree in physics in the University of Glasgow, and then, rather to my surprise, found myself in Cambridge. I didn't understand the funding mechanisms at that time, and maybe many students don't. But as a Northern Irish student, the grant was attached to me and went with me to whatever university I went to. So of course, Cambridge welcomed me with open arms. Didn't quite understand all that at that stage. I can see it now with hindsight. Turn up in Cambridge from the north, and apart from these brash young men strutting the streets, I mean, everybody's frightfully civilized. You know, you dress for dinner, this kind of thing. So I really felt quite a fish out of water in Cambridge to begin with, and even more convinced that they'd made a mistake admitting me. However, as I say, I decided that I wasn't going to walk out. I would work very hard and wait till they threw me out. And then the next thing happened. As a new graduate student in radio astronomy, each of us got given a set of tools. This is an interesting academic development, isn't it? These are actually my tools. I still have them. And they were the first tools I ever owned. I've now got quite a few more, I have to say. I'm reasonably self-sufficient. But this was also a little bit surprising, daunting. Don't know what you make of it. And I was allocated, or no, I actually had choice. I'd worked at Jodrell Bank the previous summer and they thought I had some expertise. And they gave me choice of what project I joined. They said, you know, Professor X is this project, it does blah, blah, blah. Professor Y is that project, it does blah, blah, blah. And I chose a project that was looking for quasars. At that stage, quasars, quasi-stellar radio sources, were very new. There were a number, no, maybe about a dozen at that stage. But this particular project was to find more quasars. And it did, found hundreds more. And I thought, right, that's probably a good thing to be on. But work was very hands-on, as you can see in this particular slide. Spent the first 2 years building the radio telescope with the assistance of about half a dozen blokes. And the blokes did most of the sledgehammering, but I did enough sledgehammering that playing hockey, field hockey, I could hit the ball from one end of the pitch to the other. Got quite strong. My hockey team never learnt. I was playing full back. The forwards would see the ball go past and say, oh, Jocelyn, how are we meant to get that? Watch it, you know. So besides sledgehammering, I was responsible for a lot of the receivers and the sort of the electrical side of it to make sure it all connected. And at this particular point, here's me. Not showing very well. I'm here. We're out. It's winter time in Cambridge. And the gentleman is Don Rolfe, who was the technician that was assigned to help me. And he was fantastic. He occasionally drove me mad because he was very, very thorough, very, very careful, made sure that all the electrical connections were good, you know, and wouldn't rush. But boy, it paid off. It's probably the only radio telescope in history that has worked the first time it was switched on. Absolutely spot on. At this particular point, we're putting plugs on low loss air-spaced cable. Radio astronomy signals are weak. You use low loss cables wherever you can and excellent amplifiers wherever you can, because you can lose what little signal there is quite easily. And this is a low loss air-spaced cable, which you can't coil up, or at least you could coil it in a radius of something like that, but then you can't get it in the building. So I spent one lovely winter with the cable stretched between, can't make it work, the far little red and white hut and the near little red and white hut. Post office gave us the huts, which were great. And I spent a winter working in one or other of those huts, putting plugs or sockets on this low loss cable, which couldn't be coiled up. And we finished, we believe, and we're busy checking that the connections are good. Yeah, working outdoors in Cambridge in winter is not huge fun, I have to say. It was a very big radio telescope, 4 acres, to help you envisage that, 57 tennis courts, enormous area. Cost £12,000. This was a way back in the 1960s. £12,000 went rather further, but the labor was free. It was student labor. So you weren't paying many people. Don got paid, but I didn't. And there were about half a dozen of us working for 2 years to build this radio telescope. Oh, the clicker works, great. So this is the finished article. And of course, it doesn't have a dish like you're probably expecting a radio telescope to have. It's an array of dipoles. It 2,048 dipoles, covering an area of 4 acres, 57 tennis courts. Got to keep all the bare copper wire out of the wet grass, so lots and lots of wooden posts, keeping it all, you know, the grass grows quite high if you don't mow it, sort of this sort of height, you know, waist height. So you really have to get your dipoles and feeder wire well up above that. Almost 200 kilometers of wire and cable. I didn't have to build the receivers, they were provided, but at that stage, Cambridge was still using valves, vacuum tubes. There were transistors coming in, but no, they're noisy. No, they're unreliable. We use valves. And it did have an advantage. If something wasn't working, you could simply thump the front face of the receiver, and that would resettle the valves and sockets, and it would probably then work. So we did a certain amount of thumping of receivers. But it was fantastic. Not many radio telescopes work when they're first switched on, but this one did. And it was because Don Rolfe, my technician, was ever so thorough and nearly drove me mad, but was really, really thorough. The project is to find more quasars, quasi-stellar radio sources. They were known by that stage to be very, very distant. They're strong radio sources. They must be incredibly strong at source if they're at that distance and still look strong to us. And they were distinct mystery about what they were. We now know that they're massive black holes, busy accreting material. Black holes are typically 1,000 million times the mass of the sun. So they're quite powerful things. And the way we're picking them out was a rather neat technique. So if you imagine here, there's a radio quasar way, way, way up in the sky, and the signal's coming down, coming down to, you see a little radio telescope sketched, and it comes through the space between the sun and the planets. And the space between the sun and the planets is filled with what we call the solar wind. The sun is emitting plasma, charged gas, basically, all the time. And it's not smooth charged gas, it's slightly lumpy. There are clouds which have got higher density. And that's what these blobs represent. And as the solar wind blows out, these blobs move past. And some of the time you're seeing your quasar through a blob, and some of the time you're seeing your quasar through a gap between the blobs. And so the signal you get bounces up and down. You have to be at low frequencies. I was at 80 megahertz, 81.5 megahertz. Once you get up into hundreds of megahertz, you've lost most of this. You couldn't use this technique. But observing a radio telescope through a blobby wind, some of the time the signal comes through strongly, some of the time it comes through weakly. It bounces up and down, or it scintillates. Optical astronomers use scintillate, but they're talking about light waves. This is radio scintillation. The other kind of radio source there is are radio galaxies, but they're much broader, they're extended. And so the signals from a radio galaxy would be a whole flanks of signals coming down, and you'd get some of the signal through blobs and some of the signal between blobs. And so the blobs blowing past don't affect the strength of the signal from a radio galaxy because it sort of averages out to be steady. So the technique is to look for radio sources that scintillate, fluctuate, interplanetary scintillation, or IPS. It's fairly fast, so you need a receiver that an exposure time that's quite short, so under a second. And I would typically use quarter-second integration time, maybe 1/10 of a second some of the time. Right. We see something similar on the bottom of a swimming pool. If there are waves on the surface of the pool, the wave structure focuses the light. And then that pattern on the bottom of a swimming pool usually moves along as the waves on the surface move along. So it's something a bit similar to that. Now, Quasars had been very recently discovered. The radio astronomers were finding these very bright radio objects. And when the optical astronomers looked there, they got an image of something that they couldn't really make sense of. And there's two optical astronomers involved in this story, one of whom is Martin Schmidt. It's a name you may know. He was Dutch originally, but he's working in the USA by this stage. And he's taken an interest in what the radio astronomers are finding, and they've got optical spectra of a couple of these new radio sources, whatever they are. And Martin Schmidt is trying to make sense of this optical spectrum, and he's having very great trouble. I think he had some weird substance, I've forgotten now what it was, but there was one very rare chemical element that had a spectrum a bit like what he was seeing. And they were really, really puzzled by this. Along the corridor is another optical astronomer. Aha, I haven't got that slide. Okay, let's go back. It's not going back, never mind. Along the corridor is another optical astronomer who's looking at the spectrum of another radio emitting object, optical spectrum of another radio emitting object. And he can't make sense of his spectrum either. Martin suddenly thinks, it looks a bit like hydrogen, but it's got an enormous redshift. It's as if somebody's taken the hydrogen spectrum and pulled it into the red part of the spectrum. But he thinks, does look awfully like hydrogen. And he goes along the corridor to Jessie and says, Jessie, could your spectrum be hydrogen with a large redshift? Oh, but the redshifts were scarily large. The further out in the universe you go, the further back in time you're going, the nearer the Big Bang you are, the faster are the speeds of expansion, and the larger the redshift. The redshift to make his spectrum work implied these things were hugely different, distance, way beyond anybody'd seen anything like that before. But they both, the two of them had spectra, and they both worked with large, but slightly different redshifts. So he was really quite alarmed. He went home that evening and said to his wife, something terrible happened in the office today, because he was so shocked by this large redshift implying large distance and yet a very strong source, which should have been weak at that distance, but wasn't, clearly wasn't. Yeah. What have I done now? Right. So by the time I arrived in Cambridge, it was known that at least some of the sources the radio astronomers were picking up were very distant, probably quasars. And the story started with just two of them. The radio astronomers quickly worked out that a few more of their sources probably were quasars. But Tony Hewish, who became my PhD supervisor, had the idea of specifically doing a quasar hunt, looking for radio objects that fluctuated rapidly. And to do that, you need a short observing time. So as you see the fluctuations, which means you've damaged your signal to noise, which means you've got to build a ginormous radio telescope to get enough signal to allow you to work with an integration time of 1/10 of a second or something like that. And so I arrived at the point at which they were starting to build the telescope. And you've already seen some pictures from the building of the telescope. At the point I arrived, there was a field. There was nothing in the field, but the field was owned by the radio astronomers. And Tony had put in an order for lots of wooden posts, bits of angle iron, and lots of copper wire. And half a dozen of us spent 2 years building that radio telescope. The blokes did most of the sledgehammering, but I did enough sledgehammering that I could hit a hockey ball, field hockey ball, from one end of the pitch to the other. It became very strong. And I'm actually surprised that I've reached a considerable age without, you know, a decayed spine or something like that. It doesn't seem to have hurt me doing quite a lot of sledgehammering. Admittedly, I was spared most of it. My main job was all the cables and connectors and making sure that electrically it all worked. Once it was finished building, all the others evaporated to other projects and I was left to operate this telescope myself. And it was a very, very successful project. I found about almost 200 more quasars. So it increased the sample size from about 20 to about 200, which was, you know, good, useful. And that's what my thesis had to be on, because Tony said, couldn't change a thesis title, you know, Cambridge University regulations, blah, blah, blah. From what I now know of university regulations, I don't think that's true, but it probably suited him that my thesis remained on the quasars and not the pulsars. But something happened along the way. I felt a fish out of water in Cambridge, as you've maybe already gathered. And my technique was to work very, very hard, as I've said, so that when they threw me out, I wouldn't have a guilty conscience. So I'm being incredibly thorough, really, really thorough. The telescope's been built. I've got 1 year of funding left before I have to leave Cambridge. And it's my job to operate the telescope and find lots of these quasars. And it also meant I had literally miles of paper chart because the data came out with a red wiggly line on a nice turquoise grid paper chart. And I had literally several miles of that chart paper. As a project, it worked. I found almost 200 more quasars in 6 months. Spent 6 months observing, and then the other 6 months, the last 6 months, finishing the data analysis, writing a thesis, and so on. Cambridge University at that point had one computer. It would have occupied about a quarter of this hall. It was made with what the Brits call valves, the Americans call vacuum tubes. Transistors weren't really around. And it had less memory than your laptop. And very few people could get to use it. And we didn't have time on it. We had a grad student called Jocelyn, who, instead of a computer, did all the data analysis. And this is analyzing the chart. 30 meters of that stuff came out every day during the observations. I had 5 kilometers, about 3 miles of the stuff. And I can tell you I've scrutinized every quarter inch of that really, really carefully. The main job, of course, was to find the quasars, and lots of quasars showed up, which was really, really good. And I won't go into the details, but I was able to get an estimate of their angular diameters, which was good. But remember, I'm going to be thrown out. I'm being very, very careful. And occasionally I would notice about ½ a centimeter of signal that I could not make sense of. And this is a little bit of that. We've taken out the slow drooly stuff that's the sources going by. I'm interested in the rapid fluctuations because it's only the compact quasars that will show rapid fluctuations. And this is a piece of chart, it's even got the date on it. This is the first detection of a pulsar, and that's a bit of low-level interference. And if I just take a moment to help you see the difference. You see on this one, you can see space between the spikes, whereas here, there's some space, but quite a lot of the spikes are really very close together. Here, the spikes go mainly up. There's a bit of an overshoot. Here, they go up and down differently. They look different. For those of you with a mathematical bent, what you've just done is Fourier analysis in your head. You're asking what frequencies are present and what amplitudes are present. So the maths in Fourier analysis, I always found a bit scary, but actually you almost do it automatically. They look different. So what's this? After I'd seen it a few times, I pointed it out to my supervisor and he said, "What do you think this is?" And he said, "You bloody fool." That was the normal reaction. "You bloody fool." The problem is it's all jammed into about a 1/4 inch and you can't really see what's going on. You need an enlargement. And with chart recorders, the technique with enlargement is to run the paper faster under the pen and it all gets spread out. But I can't leave the chart paper running at that speed or it'll get through a whole roll of paper in 20 minutes. And guess who lives at the observatory putting a fresh roll of paper in every 20 minutes? Yep. Next best idea, student goes out to the observatory at about this time, switches onto high speed, let it runs to about here, switches back to the normal survey speed. And I did that probably for about 10 days. And I made high-speed recordings of receiver noise. The thing, whatever it was, had disappeared. And of course, that was my fault. It's always the grad student's fault. But I persisted, and one day, something really rather interesting happened. Ignore the labeling. That's Tony Hewish's writing anyway, so ignore the labeling. The lower trace is 1 second time pips. Don't know if MSF still brought 1 second time pips, but we regularly put them on our charts. And the upper one is the signal that came in. And particularly in the middle section, you can see that it's repeating quite regularly. Goes quiet for a bit. There's a few more pulses at the right end, which seem to have the same spacing, seem to be on the same phase. And there might be 1 or 2 down here at the left, but that's perhaps pushing your luck. And it's beating with a period of about 1 1/3 seconds. So I actually phoned my supervisor up. He wasn't in a very good mood. "You bloody fool," kind of response. Must be interference. Can't be anything else. It's a huge radio telescope, an area of 57 tennis courts of radio telescope, 4 acres. It picks up everything. And this must be interference, at least according to my supervisor. Well, I know that this is keeping sidereal time. This thing, whatever it is coming back every 23 hours, 56 minutes, not every 24 hours. So if it's interference, it's somebody who keeps the astronomical clock rather than the secular clock. Well, Tony didn't believe me, but he came out to the observatory subsequent day and watched as I set up, and yet, okay, she hasn't actually crossed any wires and all that. And fortunately for me, the thing performed again, whatever it was, and he saw these pulses coming in with his own eyes. But, well, Jocelyn, keep observing it. We need to see, you know, if the period decays or how fast the period decays. Is it getting tired? Does it switch beat rate or anything like that? So Jocelyn, keep observing. And I did, and we improved the period measurement to about 6 decimal places. I'd made so many observations. And it kept coming back. So what is it? It keeps this 23-hour, 56-minute day. It must be other astronomers. But it's none of our group. We all know about radio interference. It's none of the radio astronomers. It's those flipping optical astronomers. What are they doing causes radio emission? It can't be Joe Bloggs driving down the road in a badly suppressed car, because as you know, the stars get 4 minutes earlier each day. So Joe Bloggs is getting off work 4 minutes earlier each day, 28 minutes a week. And this has been going on now for several weeks. So it's not that. It must be other astronomers. So he contacted other astronomers in Cambridge. He said, have you had any program going at least since September, which could possibly cause interference? And who's going to say yes to that? No, of course not. And it didn't stop. So it wasn't that they were causing interference and they quietly switched it off. It kept coming. So what do we go for here? Jocelyn, keep observing it. So I kept observing it. And then I began to notice in my regular data, 1 or 2 other cases where the signal looked a bit similar. So I showed these to Tony and said, I think I'm going to investigate those. And ended up actually with 4 pulsing sources, totally different positions in the sky. 3 of them pulsed with a period of 1 point something seconds. The 4th one had a period of just 1/4 second. Went bang, 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 bang. It was quite spectacular. And clearly it was going to drive the physics, whatever the physics was, because it's going so fast. I never found more than that, but I did find 4 and was regularly going out to the observatory to make high-speed observations of these things. Well, maybe Jocelyn's wired something up wrong. So at this point, Tony and I sought the help of another grad student and his supervisor. Supervisor was Paul Scott, grad student was Robin Collins, and quietly took them into our confidence. He said, look, you've also got a telescope out at the observatory that works at the same frequency, but it's an independent telescope with its own receiver and own chart recorders. Would you mind looking to see if you could see it? And Paul said yes. Robin was told to say yes. And one particular day, 4 of us convened out at the observatory. And the way the telescopes were aligned, my telescope saw the thing first, and it was pulsing nicely. And Robin's was due to see it about 5 minutes later, and we went and stood by Robin's pen recorder, and nothing happened. So Paul and Tony, the 2 academics, start walking down this very long lab saying, what could it be that showed, could it, no, it can't be that, but do you think, no, that won't work. What about, and I'm padding along behind them. Robin has stood by his pen recorder still. Suddenly there's a shriek, here it is. Robin had miscalculated by 10 minutes when his telescope would see that bit of sky. If he'd miscalculated by 30 minutes, we'd have all gone home and the story would be different. But we went charging back, and there it was, Robin's pen recorder doing the same thing. So it's not that Jocelyn's wired a radio telescope up wrong. It's not that stupid female grad student. This is real. 2 telescopes, completely independent with their own receivers, can see it. It must be out there, over, above, beyond the observatory. What is it? Jocelyn, keep observing it. Jocelyn, keep doing your data analysis. Jocelyn, do this. Jocelyn, do that. And then I suspected I had found a second one. Didn't tell Tony initially, just quietly went out to the observatory and made a high-speed recording of a different part of the sky. And in came pulse, 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 pulse. Similar, but slightly different period, totally different bit of the sky. Yay. And then I found a third and a fourth. And the fourth was really interesting because the first 3 were all beating at a period of 1 and a bit seconds, all slightly different, but, you know, between 1 and 2 second period. The fourth one had a period of a 1/4 second. So it's going bing, 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 bing. What astronomical object can do things at that speed? They're big. What the heck is this? But I managed to convince my supervisor, kept him on board, and we continued observing them. And then we decided we had to write it up. We wrote up the first one first and said we've got another 3 and there's another paper following. And just before the paper got published in Nature, Tony gave a colloquium in Cambridge and gave it a very titillating title. And every astronomer in Cambridge came, including Fred Hoyle, which is a name some of you probably know. Fred did not like the radio astronomers. Fred had his pet theory called continuous creation. The radio astronomy data was suggesting that the Big Bang was the right theory about the origin of the universe. And Fred did not like this and therefore did not like the radio astronomers. And anything he can do to discredit the Cambridge radio astronomers, Fred was up for that. So Tony gave this colloquium, gave it a very titillating title. Every astronomer in Cambridge, including Fred, came. And when Tony had finished speaking, Fred spoke. Now, we weren't really very clear what these things were. It obviously had to be something small. The smallest thing known at that stage was a white dwarf star. And Tony's favorite model was a white dwarf star that oscillated. And as it oscillated, somehow launched shock waves into its atmosphere, which somehow, even more hand waving, gave pulses a radio wave. So it goes pulse, 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 pulse. And Tony put forward this model. We subsequently were able to test the models, and I'll try and remember to come back to that. But anyway, Tony put forward this model. And having done the talk about what we'd found and what Tony thought it was to all the astronomers in Cambridge, because Tony had given this very titillating title, Fred Hoyle was the first to speak when Tony finished, and Fred said, "I don't think it's an oscillating white dwarf. I think it's a neutron star." And Fred was right. In 40 minutes, he had absorbed all this new information and hit the right explanation. Now, he may have been a cussed Yorkshireman, but he was a darn good astrophysicist. Fantastic. So we published the paper about the first one. It came out a few days after that colloquium, and followed it with a paper with the other three that I had found. And the press got quite interested. When they discovered there was a young woman involved, they became very interested. So Tony would be out at the observatory talking to some of the journalists, and my phone back in the lab would ring, and Tony would say, "Jocelyn, take a taxi out to the observatory. The journalists want to meet you." Or more particularly, the photographers want to meet you. I was the sex side of the story. So please could I do some buttons on my blouse, and, you know, how many boyfriends did I have, and would I describe my hair as blonde or black? Nothing else was allowed. What were my bust, waist and hip measurements? Really serious astronomical questions. And Tony dealt with the astronomical questions. I found it a bit revolting. You know, young women weren't allowed to be scientists. You were just sex objects. So one of the science reporters that interviewed us was from the Daily Telegraph. And they did, my politics aren't Daily Telegraph, but they had good science coverage. And we had an interesting discussion with that journalist, because he said to us, "What are you going to call these things?" And we had thought fairly carefully about this. We avoided the word pulsed, because it might imply somebody or something was making the pulses. So we said pulsating radio sources. He said, no. Oh my God, it's too long. We need something shorter. We already had quasar. And he said, what about pulsar? And pulsars they became, thanks to the science correspondent of the Times. Or was it the Daily Telegraph? Daily Telegraph, Anthony Michaelis. So a lot of interest in these results. A lot of rather crazy interest in the young women involved. It was quite hard to be a professional scientist. You were there for the sex, which was annoying and a bit degrading. Anyway, just to finish off with a bit of proper science, what are pulsars? We now know that they're very, very compact objects, so compact that the normal atoms have broken down, and they're made largely of the fundamental particle called neutrons. They weigh something comparable to the sun, but they're only 10 kilometers radius, about 10 miles across. So they're very, very dense, very, very compact. They are formed when a massive star explodes at the end of its life, what's called a supernova. In the explosion, the core of the star gets kicked against and gets compressed way down to 10 miles across. And it spins quite fast because when you compress a spinning object, it spins faster. It's got a very strong magnetic field, and the magnetic field is offset from the spin axis, as you see in the right-hand image. And we believe that the radio beam comes out probably from the magnetic poles, although there are still some people who say it doesn't. Oh, sorry, it's not working. There are some people who say it comes out at the equator. But anyway, it's linked with the rotation of the star. And once you get a star rotating, it's quite a job to make it change its rotation. So the periods, you can easily measure them to 6 or 7 decimal places before you see any change. They do very gradually slow, but as I say, it has to be in the 6th or 7th decimal place before you can see that. So we now believe that they're very rich in neutrons. So we call them neutron stars. And yes, they're about 10 miles across, and they weigh a bit more than the sun, probably about 1.4 times the mass of the sun. When you put that much mass into a small ball, the gravitational field, the gravity is very, very strong. They also have strong electric and magnetic fields. And as you've seen in the last video, they're spinning quite fast. Typically, they spin about once a second. There are some slower, but younger ones spin a good deal faster and then gradually slow. We now believe that they are the core of a star that exploded as a supernova. And in the explosion, the core gets kicked against and gets compressed down to about 10 miles across. And the main way to observe them is as one of these pulsating stars. And I don't know, I don't think the audio link will work. I've forgotten to set it up. No, never mind. A slow pulsar, you hear clonk, 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 clonk. A fast one goes whee. So the fastest ones have about 1,000 revs a second. Really fast. And that gives you that wonderful note. They're primarily seen in the radio. 1 or 2 are in the visible, including the one in the Crab Nebula. And there are some stories in our history of people at a popular observatory in the USA, open night, telescope set on that funny star in the middle of the Crab Nebula. A public step up to the telescope and say, oh, gee, wonderful, you know, whatever they said in 1950s USA. And a young woman steps up to the telescope and says, that star's flashing. And the patronizing night assistant sort of says, no, 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 dear, it could be. And she says, my job is as an airplane pilot. This is the 1950s. My job is as an airplane pilot. I fly planes from the manufacturer to the customer. I fly at night. There's not much to do in the cockpit at night. I look at the stars. That star's flashing. It turns out that some people have sufficient, I guess acuity is the word, that they can see flashes at 30 times a second. And it tends to be young women who can see it. I suspect she saw the crab pulsar flashing from her aircraft cockpit at night. These things are formed in what are called supernova explosions, and this double slide, which I'm sure a lot of you will be familiar with, is the supernova that there was in the Large Magellanic Cloud in 1987. So this is the before photograph, arrows added after the photograph's taken, and that's when that star had exploded. I don't know how many of you have managed to see a supernova with your own telescopes, but it must be quite awe-inspiring. Crab Nebula, very famous supernova, 1054 AD. There's a pulsar in the middle of it. Yeah, pretty well in the middle, which you don't see in the optical, but it's up there. And it's a fairly fast one, fast pulsar, because it's relatively young and hasn't slowed that much yet. Goes 30 times a second, this particular pulsar. Right, how are we doing for time? You okay for another few slides? Thank you very much. Okay. One of the nice things about having discovered pulsars is every so often somebody comes up to me and says, you know, I nearly discovered pulsars, and tells you the story. And these stories tell us so much about how we do science that I'm going to repeat some of them for you. I've already said a little bit about the first one. This is the young lady who flies aircraft from the manufacturer to the customer, flies at night. It's open night at McDonald Observatory, and this telescope is being used to show the public interesting things like the Crab Nebula. There's a young man called Elliot Moore. He's still a student, but he's working at the observatory as a summer job. And he recorded this conversation and would tell the story again. So this female, who's actually an airplane pilot, steps up to the telescope, which is focused on the Crab Nebula, center of the Crab Nebula, and says, that star's flashing. And the night assistant starts explaining about scintillation and turbulence, and you know the story. She says, no, I fly airplanes by night. It's my job. There's not much to do in the cockpit at night. I look at the stars. I know about the scintillation of stars. That star's flashing. Now, the Crab pulsar flashes 30 times a second, and that's very close to the limit of what the human eye can see. But it tends to be young women who are best able to see those high frequencies. And here's a young woman saying she can see it flashing. I'm pretty certain she did see it flashing, but nobody took much notice. What the hell, a young woman? The student remembered the story, Elliot Moore, and told it. Nobody believed her, nobody followed up. The Australians in 2007 get a very excited email from an elderly US gentleman. He said he'd worked for the US Army. Well, he had to do military service. He was posted to Alaska to the early warning system there, looking for missiles coming in from Russia, Soviet Union. Not a lot to do. He was allowed to play with the radar equipment when things were quiet. And he's done a university degree. He's done an astronomy course. He knows about right ascension declination. And as he plays around with the radar, he finds some pulsing sources in the sky, including the Crab Nebula one. And he makes a rough note of the right ascension declination of these pulsing sources, and illegally takes that bit of paper away with him when he leaves the military. Donkey's years later, he's found the online Australian pulsar catalogue, and several of his pulsing sources are in it. Contacts the Australians. Whoops. Yeah, okay. He contacts the Australians, who kind of check him out and decide he's genuine. If that hadn't been top secret military, we would have discovered pulsars. I don't know, 1950, no, 67. Okay, it's about the time we did discover pulsars. He made contact with the Australian radio astronomers and came to several of our conferences in a great state of excitement. They checked him out and I think it's genuine. So he's the gentleman at the far end of the table there. Another example, Sue Simpkin tells this story. She was asked by Low Vulture, the gentleman in the picture, very famous Dutch astronomer. She had some time on an optical telescope and he asked her to take an optical spectrum of that funny thing star in the middle of the Crab Nebula that we suspected was the remains of the star that exploded and created the nebula. And Sue does that, and she says the spectrum's pretty dull. But as she was observing, she could see a very rapid flickering. And she mentions this to Low Vulture when she gets back. He says, no, it couldn't be. The mains power supply in Canada used to be at 50 hertz. Some young women can see 50 hertz. There are a number of female Canadians who, as young women, could see their lights flickering. Sue Simpkin was one of them. Sue Simpkin can see 50 hertz. Low Vulture asked her to take, would she mind when she's observing, take a spectrum of that funny star in the middle of the Crab Nebula. It's known as Minkowski's star. So Sue obliges, and when she gives Low the data afterwards, she says, you know, it looks to me that that star's flickering. And Low says, no, couldn't be. Didn't believe her. So she didn't publish it. But she knows she can see 50 hertz because she was brought up in Canada. And whereas a kid, all the lights and everything were flickering at 50 hertz. So actually, we think she saw it. But Low not believing her was sufficient to prevent her pushing the story more. When finally that pulsar was discovered and was found to be flashing, he admitted that, yep, you probably saw it, Sue. The final example is from radio astronomy. Radio astronomers were making a catalogue of the whole radio sky at, I think, 408 megahertz, yes. Getting grants of time on big radio telescopes wherever they could. And it's really painful doing a whole sky survey when you're getting bits of time here and there. But they've nearly finished. There's a few little patches of sky that they haven't surveyed, and they're busy mopping them up on a radio telescope. I can't remember which. It's before computers were widespread. They're using pen recorders. And one of the pen recorders was a bit sticky. It occasionally sort of went, you know, carried on. And in the early hours of one particular morning, that pen recorder started going wheep, 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 wheep. And the radio astronomer in charge said, oh, damn that pen recorder, and did what we always did to pen recorders, thump it. And it stopped going wheep, 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 wheep. She said, oh, good. Put on his coat and went home to bed and did not make an entry in the logbook. If he had made an entry in the logbook, they could have claimed prior discovery of pulsars, because he was actually observing one of the pulsars when the pen went wheep, 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 wheep. Here's your logbook. Yeah, I think, yes. And the other thing was, by the time pulsars was announced, the group doing that work had disbanded. So none of them felt that they wanted to go back and look through all their survey data and see if they could see any pulsars, which they would have had they done so. Okay, it's time I sort of wind up. Factors that led to the discovery of pulsars when they were discovered. We had our own radio telescope and our own receiver, and we weren't sharing it with anybody. And it was my job to understand its foibles, why it behaved the way it behaved. And I'm a grad student, a research student. So I've got no other responsibilities other than my research. I've got time to follow up anomalies. And I'm being actually very, very thorough, because I now recognize I suffered with imposter syndrome. Remember, I'm not bright enough to be in Cambridge. They're going to throw me out. They're going to discover that I'm stupid. Classic imposter behavior. If you know anybody, maybe somebody starting high school or something, says, I'm not bright enough. Don't try arguing them out of it, but tell them to work very, very hard so that when they're thrown out, they won't have a guilty conscience. And they'll discover something and they'll do fine and they won't be thrown out. That's, I think, the best way to deal with imposter syndrome. Okay, maybe they will throw you out, but until they do, you do your utmost. You do your very best. There weren't, as far as we knew, other observers doing similar work at that time. So we weren't sort of feeling, I wonder if the Germans have found something. We didn't dally, but we didn't have to rush and take shortcuts. We could be thorough. It's not an optimum frequency, 81.5 megahertz for pulsar work. And the first source we discovered wasn't the strongest pulsar out, but we found him. If you're going to find something slightly outrageous, it's good to have a good address. And Cambridge is pretty good. Oxford's not bad either, but you know, it's okay. Research councils have had comes and goes a bit, but they ask you to declare the objectives of your research when you get funding. And then your performance is measured against how well you met those objectives. This couldn't have been one of our objectives. We didn't know these things existed. Would that system have marked us down for deviating from our declared program? It just might have. How crazy can you get? And if we had computerized the research, it wasn't an option at that time. Cambridge had one computer. It took up a whole room. It was made with valves, vacuum tubes, not transistors. And very, very few people could have time on it, less memory than your laptop. So we couldn't have computerized it. But if we had been able to, and if we had computerized it, would we have programmed the computer to look for something? It might depend how much spare memory there was, to be honest. I want to pay tribute to an Italian astrophysicist, Franco Pacini. A few months before the discovery of pulsars, he had an important paper published in Nature, which is the leading English-speaking language for research. The Crab Nebula, very pretty, I'm sure a number of you looked at it. There was a question about why it was still shining. It was the remains of a supernova that exploded in 1054 AD. And 1054 AD is quite some time ago, and that nebula really ought to have dimmed. Why was the nebula still so bright? Franco puzzled about this and published a suggestion that there could be a not yet discovered kind of object called a neutron star, the core of the star that's left after a supernova explosion. If that neutron star were highly magnetized, and if the magnetic axis was offset from the spin axis so that it coned around as the star spun, then you might get magnetic dipole radiation coming from this object. He thought probably that the magnetic dipole radiation would be at a frequency that couldn't escape from the nebula. So the energy would be dumped in the nebula and it would keep the nebula shining, which would explain why there was still a nebula centuries after 1054 AD, because it normally would have expected to have dimmed. Something was keeping that Crab Nebula shining. Well, he was absolutely right. We now know that in the Crab Nebula, there is a pulsar, which is a neutron star, which spins with an inclined axis, produces a radio beam that keeps the nebula energized and shining. Alas, he wasn't around to see the discovery of pulsars, but he was very, very right. So we've had a little pulsar group in Oxford. This is us outside our building. Thank you for your interest. Thank you for your attention.